Hello everybody, 7:30, let's get started and let's see. Tonight we were supposed to, sorry for that, we are supposed to discuss about the multiplier and division. Anyone has any question on that part? Let me also go to the discussion section and see if there is any. Or any other questions. If you have, you can bring it up now. Okay. All right, since you don't have question, let me focus tonight on this combinational multiplication, and let's try to understand that one. The one reason why I want to do that, because building up a combinational multiplier is part of your project 3. So you need to have a very good understanding of what is that multiplier component look like. Let me share my screen with respect to discuss that one. And I'm talking about this faster combinational multiplier for us. And this is example of 32-bit multiplier. But in this class, let me pick up a smaller multiplier, 4-bit multiplier, right? So for 32-bit multiplier, we need 32-bit adder. So similarly, for a 4-bit multiplier, we need 3 4-bit adder, and we need to connect them together. And I have defined a gate level simulation model, like I'm showing in this model sim window, and it is using a 4-bit ANDs. So both of the inputs are 4-bit each. So inside that implementation, it has actually 4 AND gate. Like we can look at that implementation itself a little bit. So each of these input is 4-bit and output is also 4-bit, but output is 4-bit, but internally it is actually instantiating. It has like 1-bit, 2-input, 1-bit AND gate, and combining them, it become a 4-bit, 2-input AND gate. Okay. So that's not complex. Then let's discuss this part. Like it uses like 4 stages of AND, similar to here they are using like 32 stages of AND, of 32-bit 2-input AND each stage, and then it uses 3 of the 4-bit adder for the 4-bit multiplier implementation. And this part is simply like, you can think of it as collecting the signals from the various output of these components and putting them into a nice result output bus through using the buffer gate. You all know that buffer is not a logical manipulation. It's simply a equal to a function there. Electrically, it has significance. It bumps up the strength of the digital signal. So for a physically long running wire from one logic place to another place, some buffer, sometimes we insert buffer to strengthen the electrical signals value onto the line, but it doesn't have any logical consequence or logical operation in the circuit. Anyway, that's a different story. So here, now let's try to understand what this part is trying to do. And I'm trying to draw the equivalent circuit, logic circuit in the whiteboard. So it uses, just let me pick up my drawing board there, just hold on. Okay. So, how do I write? Okay. So it has 4-bit AND with one part multiplicand, which is like all 4-bit, okay, and another part is the 4 replication of the multiplier PLR LSB 0th bit. So this is almost like taking 1 bit and replicate like 4 times. Okay, something like that. So instead of drawing that 4 line there, what I will draw is simply something like this. So it's the 1 bit, and somewhere we are replicating it into 4-bit signal. So this part is mainly that transition part, like from 1 bit it becomes 4 bit. The same replication. Just a notation of the notation of the diagram. That's all that convention is. Actually, I've started too much left. Let me just shift it towards the right. So here we are. Okay, multiplier. Okay, 1 input. This is 4-bit. It is coming from MPLR multiplier 0th bit and replication. And then another one is coming from multiplicand. The whole, all 4 bits together. And from here, it's coming out a 4-bit result. Out of that, 1 bit is going as my result. Multiplication result, bit 0. And rest of the 3-bit, so this is 3-bit, and then add with a 1-bit 0, it becomes 4-bit, and that is being fed into an adder. Okay, an adder. What is the other side of that input? What is the other side of that input? Is this one. Another AND, 4-bit AND, coming from replication of multiplier of first bit, bit 1, and multiplicand. They're all 4 bits. And that entire 4-bit is being fed into the adder. Output of the at the second end. Now, now this guy has 2 things. One is the 4-bit output, and other is the carry out and sum, right? So from there, we are picking up 1 bit LSB as a result, bit 1, and the rest of the 3-bit joined by the carry out, making the 4-bit, and it's going into another adder. Okay. And what is the second operand of that adder? Is replication of multiplier bit 2 with all 4-bit of multiplicand and going as a 4-bit into that adder. It has a sum bit, carry bit, 4-bit out. LSB is coming out as result bit 2, and rest of the 3-bit is being fed into the next next adder by joining the carry out from here and this is coming from another end, replicated this MPLR bit 3 with enter MCND 4, okay, and this one is 4-bit. 1 bit is going out as a result 3, and rest of the 3 bits along with the carry out, they are basically your result of 4, 7 to 4. Okay, so together those 4 bits are constituting your bit 7 to bit 4 of the multiplication result. So entire thing is become like a 8-bit result out of this 4-bit multiplier. Now, how we put that into Verilog, that's the next question. But before I jump into that, any question from anyone about this diagram? Okay, then let's see what goes where. Okay, now this 4 AND is basically these 4 ANDs, and what are they? You see there are a bunch of 4-bit signals here, right? Coming out of the adder, 4-bit, coming out of the AND, 4-bit. So instead of writing many variables, what I wanted to do there is basically define all the AND outputs as an array. So this is a 4-bit output, 4-bit wire of 4 elements, right? This is the 4 elements group array. Since there are 4 and since there are 3 adder, so we need to have a 3 element array of adder output. Each of them are 4-bit wire. So this is what I just written down as to save my writing of the variable names. Similarly, for the carryout, we have 3 carryouts. Carryout here, 3 carryouts. That's what this guy wants for. This is an array of carryout signal. It is, I could have done it like a bus way, like it's a 3-bit bus and do that, but I can do it in the other way also. There is nothing right or wrong there. It's just an array of wire of 3 elements. And then as a first AND stage, 0, which is this one. This is your 0, okay? And then it's the 4-bit replication of the multiplier 0 with multiplicand. Exactly what we are doing right here. And second one is, this is the number 1. This one is basically replication of multiplier 1 here, 4-bit, with a multiplicand AND. So similarly, the 3rd and 4th AND are basically the same way you can think of. And on the adder side, now what we are doing, look at here. So this is my adder instantiation 0, which is here. And next one is 1, which is here. Next one is 2, which is here. And then you see first adder is coming from three most significant bit, okay, joined by a 1-bit 0. That is constructing the 4-bit. Exactly what we are doing here. Look at the first stage and output, taking the higher 3 bits and then prepending with 1-bit 0. And the other input to the adder is coming from the second stage output, all of them. So and out 1. And then overflow is connected to the carryout signal here, carryout where 0, and the add output 4-bit, this guy is here. And then what happened to the next one? See, it is basically carry out and 3 MSB of the previous instruction. So previous output of the adder, previous stage adder. So I am doing that by adder output 0. So this is the adder output 0, add output from stage 0. I am picking up the MSB side 3-bit with appending the carry out of the stage 0 adder. The second input of the addition is coming from the AND out, this one, right, of the second stage, number 0, 1, 2, yeah, the 2 stage. And then it's added, its output is the add out of the stage 1. And similarly, the next one is also like it is coming from the stage 1 adder output, picking up the higher 3-bit of MSB and carry out, prepending with the carry out, with the and third stage output overflow is going out as a CO2, and then output is all this thing. And then we are constructing the result, right? The first one is the LSB of the first stage AND. So this is what is happening. Second bit is the LSB of the first stage of add. This one. Next one is the LSB of the second stage of add. This one is the LSB of the third stage of the AND. And then these 7, so bit 4, 5, 6, 7, those are respectively the adder second stage output bit 1, bit 2, bit 3, and carry out. So it is purely by this logical connection we have implemented this multiplier, 4-bit unsigned multiplier. Before I go to the simulation result, is there any question? Okay, so now since we convinced that this is the one, this circuit, what we have written in the gate level is same as what we intend to do here, let's try the verification through the simulation. On the test pen side, what we have, very simple, we instantiated that multiplier and simply trying to multiply from 0 to 15 with 0 to 15 in a loop, like just all the numbers in between we'll test, and we'll just look at the sample result and make sure they're correct. So we compile it, and then we pick up the right module to simulate, which is multiplier test bench. Let's load it, and let's we can simply just look at A, B, and Y, these 4 values, add to wave. Okay, and then simply simulate. Okay, we are end of the simulation. Let's look at the result. Okay, all right, there are a lot of numbers. Let me first change the radix of these to maybe unsigned. Okay, so first A is looping through 0 to 15. And then if we just expand, yep, okay, so this guy also looping through for each of the value of the A. B is looping through 0 to 15, and Y is simply the result of these two multiplication. So yeah, initially we see 0 multiplied by anything is result 0. 1 multiplied by anything is that number, so it is following. Seems like this is good. Let's just randomly put something like 9 maybe. 9 multiplied 0 is 0, and 9 multiplied by 2, 18, 27, 36, 45, 54. Yeah, seems like correct. How about the other end? 15 multiplied by 0 is 0, by 1 is 15, then 30, 45, yeah, 60, 75, 90. Yeah, seems like all the way till 15 by multiplied by 15 is 225. That seems like correct. So see that like just by combining different combinational gates, as in here, here's my multiplier here. Like see that we have used like 4-bit ANDs and adder, simple adder. It is not add subtraction circuit, it is simple adder circuit. And then if you drill down into each of them, your AND is simply like 2-input single bit adds, combination of that. And under that AND, you have basically basic level implementation of the NAND and NOT. And NAND and NOT, you can do it with transistors, right? They're just a bunch of transistors there. And similarly with the adder circuit as well, like if we open up that, a full adder RC, this bit is basically, we are combining full adder, 4 full adder and 1-bit full adder. 1-bit full adder is nothing but some OR and some 2 instantiation of half adder. Each half adder is nothing but XOR and AND. And each of them has a transistor physical implementation using NMOS and PMOS. So this entire multiplier circuit that we have developed is practically is a network, is a giant network of transistor, PMOS and NMOS. And simply by sending electrical signal, which represents the decimal values, we are getting output, like some bit manipulation runs through this network maze of the transistor and giving us the right value of the result at the output of this circuit. And conceptually, there is nothing arithmetic operation about that. Everything is logical operation inside, and we are manipulating through the binary logic, Boolean logic to produce multiplication result. I feel personally this is very amazing thing to think of, even like some electronic circuit crunching the bits, crunching the representation electrical signal and giving us some arithmetic result. This is a huge, huge step. So think through, like when you have time, philosophically think through how far we have been evolved, like from an ancient abacus style calculation versus the modern electrical computer, just using a basic electrical component of PMOS and NMOS in our computing system. Question? Okay, if we don't have any question, then what we can do, let's calculate. So we know this 32-bit adder, right? Let me just put it on the whiteboard, that picture. Okay, download. And what we essentially do, we want to see how much area that multiplier will take in terms of micrometer square. Just like we did, remember last day we did area calculation of of the adder subtractor circuit. We'll do the similar exercise here. That first of all, we'll ask ourselves how many NANDs we need to implement this one, and then simply multiply the NAND's area, one single NAND area, then we map it down to how many transistors we need, PMOS, NMOS, and then simply multiply that with the area of the one single transistor to get the number. So let me first put the picture down there so that you have a reference. Also, you can look at your slides, of course, or notes. Okay. So there, and here, remember, it is not addition subtraction, but it is simply the adder circuit, RC Ripple Curry adder, and use the four NAND gate implementation of the XOR as we did earlier, and just do the similar calculation as we did earlier for one adder, then come back with the this circuit. So main problem is this. First of all, for a NAND only implementation, how many PMOS, how many transistors are needed, and if each one has, let's say 20, if each transistor takes 28 nanometer by 28 nanometer space, how much space is needed in micrometer square unit? Okay, for NAND implementation for 32-bit unsigned combinational multiplier. Okay, so for 32-bit unsigned combinational multiplier, how many transistors are needed? If each transistor takes 28 nanometer by 28 nanometer space, how much space is needed in micrometer square for this circuit? Let's do it in, I was not sharing my screen, right? Sorry for that. Let's do this problem in a group, and the breakout room, let's see, 10. Okay, study group 10 has a one participant. I'll move that participant to other room, maybe SG14. SG10 to SG14. Okay, and let's take, let me see, others has at least more than one student. Okay, let's take 10 minutes to do this before we return into our discussion to see at least the approach, and if someone have calculated it. So 10 minutes from now, open room to all, and then you move to SG14. Okay. Okay, I believe all of you are back from the breakout room, and let us turn to how about study group 3 to see if they have come to a conclusion or at least explain what their approach is. Jordan, Mike, Christopher, Tom, Brian, Tran, that group, study group 3.
We weren't able to finish, but we can show what we did so far.
Yeah, sure. You can share screen if you want. I have turned on the share screen.
All right, what we did was um the multiplier from the diagram, it's 33 nans and then 31 32-bit adders. And then each 32-bit adder is 480 nans. So then we got the total number of nans is 14,912. And then we're going to get transistors from there and then figure out the area.
Okay, the approach is correct. How did you get the total number of NAND as, how many you said?
33 nans and 31 32-bit adders.
33 NANDs. Why you need 33 NANDs?
Or from the diagram, it looked like the first level was 2 nans and then there was 32 levels.
Actually, you have 31 level.
Oh.
Yeah, so remember like in the previous like 4-bit adder, 4-bit multiplier, we showed that it has 3 adder and 4 AND, right? So you scale it to the 32-bit, that becomes like 32-bit and 31 32-bit adder.
So it's 31 adders and how many nans?
32 of 32-bit AND. Your approach is correct. Like you basically at the end of the day, you want to go through the number of NANDs multiplied by 4, which gives you the number of transistors, then multiply by the area, that will give you the area. But yeah, just look at the circuit and you need to tune up that number of and NAND gate you come up with, okay?
Oh,
All right, let me actually try to solve on the whiteboard and see if you agree with this solution. Okay, let me see. Where is my? Okay. All right. So what we have here, as you said, one adder, one 32-bit adder. It's basically from the previous day's problem. So one 32-bit adder is like it's basically 480 nans. Okay, now that means you have total 31 adders for a 32-bit unsigned multiplier. 31 adders has 31 multiplied by 480 equals, it comes down to be 14,880 nans. And on top of that, you have 32-bit 2-input AND. It basically, that is equivalent to 32 multiplied by 32 ANDs, and each AND gate is a combination of two NAND gates, like one NAND and one NOT. So that becomes 32 multiplied by 32 multiplied by 2 NANDs, and that is basically gives you 2 to the power 5 multiplied by 2 to the power 6, 2 to the power 11, 2048 NANDs. So total you have then 14,888 plus 2048, which is equals 8, 2, 1, 16. Okay, 16, 9, 2, 8 NANDs. Just take a calculator to make sure it is the correct. 8 plus 4, 12, plus 1, 9, plus 2, 4, 6. Yeah, seems like correct. And then, so the total area, so total number of transistors would be then the 16,922 multiplied by 4. Like each NAND has 4 transistors in it, which will become like, let me use the calculator, 16,928 multiplied by 4, which is 67,712. 712 transistors. That means area would be 67,712 multiplied by 28 nanometer multiplied by 28 nanometer, which is, again, let me use a calculator, multiply 28, multiply 28. Okay, 53 million 86,208. 86,208 nanometers square. And to convert it into the micrometer square, what you need to do is divide it by 10 to the power 6. This 3. So it's approximately 53.09, almost like 53.09 micrometers square. So that would become the footprint of this multiplier, which needs almost like a 53 micrometer square space for a 32-bit combinational multiplier implementation. Question? Okay, then let's take 5-minute break, like 8:23, 24. About that time, we'll be back. Okay, let's get back into our discussion. Let's start with the pop quiz. Please go to the canvas, find out uh, your pop quiz number 4, right? Isn't it? Yep, today is March 9, right? Yeah, pop quiz number 4. And I'm launching the poll to make sure everyone is ready to grab the password. So pop quiz launch. Let's see. Okay, 32 of 43 said yes. 34 of 43. 39 of 43. Almost there. We have 43 participate tonight. Okay, I think let me share the password now. Here it go.
Professor,
Yes.
could you please show me the password again? I clicked on yes, but it didn't work for me.
Oh. Okay.
Sorry about that.
Let me see. What's the name?
Rohi?
Arohi. Okay. Chopra?
Yes.
Okay, let me just send you over the chat.
Thank you.
Just hold on. Did you get it?
Yes.
Try it out. Okay, I think for most of you, it's done. The quiz, let me share the stat first. Let's see. Screen. Okay, this is alarming. Average score is 49%, high score 90%. That's okay. This the high score, like I expect 100% as a high score. But this is definitely as a group, the whole class will actually trailing behind. So please keep up your pace with the study of these classes and subject, and make sure you are up to the point, up to the latest and greatest lectures that you are supposed to review till now. Anyway, saying that, we will be starting the real architecture subject now. Okay, so we are at the end of the this. It is almost like a review, at least like I believe 75 to 80% of this material so far we have covered is also covered in my CS47 class. So for my former student, is not that unfamiliar territory. For others, you have covered these already, so you are on the same stage as my former students are. Now we are actually starting the hardcore architecture subject. Okay, and that's what we'll still on the module 4. We want to review this lecture 11a. It's a part of lecture 11. Lecture 11 is all about how do we build up a full processor, microprocessor based on a given instruction set architecture. So that's the whole topic in this lecture and the next module, the processor design, which has only one lecture. So it's a long one. So we have like, we'll break it evenly on 2 days. Like next day, please review the ALU design part, which we will talk about how the sequential ALU is designed and implemented, and with some state circuit and diagram. It has only one lecture video there. Please make sure you go through that, and then you go back to start with the next module. Please first visit this module introduction page, this video, and then start with the next one, 11, lecture 11. For the next day, both ALU and I would expect you to cover up at least these two, part 1 and part 2, microprocessor design process and instruction fetch and R-type data and control path design. So if we hit that target, both target by next day, then the day after, the next coming Tuesday, would become like part 3, 4, 5, and 6. So part 3, 4 is more like a construction of the I-type data and control path, and then J-type data and control path. And then we have some quick conclusion about the design process of this processor. And then we have an optional part 6 of micro instruction code generation. This is optional for time being, but it is much needed for your project 3 completion. Okay, so this is an important discussion. I would encourage you to go through that as well as soon as possible. Okay, just don't keep it for the last minute. Okay, but it is optional for this discussion, at least lecture 11, but this part 6 is very much needed for your project 3 completion. So make sure you also go through this one at some point of time. Now, what are this about? ALU is easier side of the whole story, but the microprocessor design process is mainly, we remember in the instruction set architecture, we have 3 type of instruction: I-type, R-type, I-type, and J-type. For each of these set of instruction type, we'll break them up into pieces. Like, first of all, each of this type are a dedicated circuit. We'll start with that concept. It's a dedicated circuit, logic circuit. And each logic circuit has two parts in it. One is the data path, where through which data or information being crunched, processed, manipulated. And other part is the control part, instruction path and control path. This control path is more like how do you control the data path element throughout this data crunching process. So your processor is basically split up into this part of the circuit, like which supports R-type instruction, which support I-type instruction, which support J-type instruction. Each part has two subparts, data path and control path. Data path is how the logic goes through and being manipulated through different logic component. And control path basically says how these data crunching elements are being controlled in a time way. Okay, that is the controller path. So once we understand that, then we actually put together these three-part circuit on top of each other and optimize them. We don't need like 3 ALU, we don't need 3 register file and so on and so forth. We just make it into one big circuit with using many multiplexer around this data path at least. Okay, so that's a very fascinating idea to start with, complex idea. So make sure you are up to all this lecture, you're up to date on all this lecture and understand and ask me as many questions as comes in your mind. Okay, so it is a very complex. Make sure you are clear on the concept. Question?
So the pop quiz will be available after class?
Yes, I will.
Okay, thank you.
All right, if there is no other question, let's end tonight.